Okay. Good afternoon to everyone.
So we need to see some new material today, right? New concepts on that.
Yes. Okay, I'm going to share my screen. Okay, do you hear me?
Yes, profe.
Okay. Uh,
But we don't see your screen though.
okay, I'm gonna share the screen. Uh, okay.
I guess he's having some connection problems, right? Because just got out of the meeting.
Probably. Probably.
Okay, so meanwhile, oh, you Jairon has some connection problems as well. And welcome back.
Okay, there's a problem when I try to share the screen. It gets me out of Google Meet. Give me a second. Uh, I'm gonna share the screen. Okay. Do you hear me?
Yes,
Yes, profe.
Okay, okay. This is the web page, okay?
yes, we can see the web page now.
Okay. Uh, okay, the first thing that I have to tell you is the following. Uh, are you seeing here this link?
Centrality measures.
Yes.
Yes.
Uh, if I click here, let me click here a moment. Do you see what happens?
Error.
An error.
Okay, for some reason, I don't know what reason, these slides were lost. I think I was working with these slides 2 or 3 hours ago in my university, and they get lost. Okay, I want to tell you if some of you has downloaded these slides. It's a zip file. If not, I'm gonna use slides in Spanish that I have the earlier version of the slides. Okay? I don't know if you understand me.
Yes, I guess it's clear. I hope they can understand the
Okay, I didn't know what
Spanish
happened. It was the
slides.
Dropbox. It was my fault. I don't know, but this slide disappeared. So if any one of you have downloaded these slides, you could send it to me, the zip file. If not, I'm gonna work with other slides. Okay. So, okay. Uh,
Yeah, it sounds weird, but I'm sorry. Yes, indeed, that you lost them.
no problem. No problem because okay, it's not a big problem, but in that case, uh, I, I'm gonna begin with the slides in Spanish that I have. The earlier version of these slides are in Spanish, but I'm gonna talk in English. Okay?
Good.
Okay. Uh, I guess they are here. Medidas centrales. Okay. Centrality measures of a network. We're going to talk about four principal centrality measures, and we are going to understand it. And then we are going to do a workshop, a small workshop of 15 minutes. And later on, we are going to talk about global measures of a network, okay? So the session of today are local measures of a network and global measures, okay? Okay. What are the objectives of these measures? As we saw last session, uh, one objective is trying to identify the important nodes of a network, okay? These have a lot of applications. We're going to see some of these applications. Uh, Vulnerability of a network. Vulnerability when we have a transport system, an urban system, when we have internet, how vulnerable is internet? Another application, important application of these centrality measures is diffusion of information in social networks, in enterprises, and a very important diseases, biological contacts and infections, okay? I'm gonna hide this. Let me see this model a little bit. I guess this is, okay. No, this is not, no, excuse me. Okay, types of centrality measures. The first one, the most simple and the most important, we have talked about it, okay? Degree centrality. Before I continue, if there is any question at any moment, you could ask me, okay? Uh, Degree centrality. The links of a node increase her importance if there are more links that go out of the nodes. Intuitively, if you have a social network, a big degree centrality implies, for example, a lot of friends, but also implies that if you have this in a social network, this node, and had a lot of degrees, you could send information, and the information go to many people, okay? Here is an example. I don't know if it is clear. Here is a simple network, and these numbers are the degree central, the degrees or the degree centralities of each node. It's very easy to calculate, okay? We have here at the left degree centrality, absolute degree centrality. At the right, we have relative degree centrality or normalized degree centrality. Could you tell me, please, these numbers, one half, one sixth, how are calculated? Someone could tell me? I don't know.
Hello, anyone?
Anyone?
Anybody home?
Why it's here 1/2? Why here 1/4? It's clear or not?
Yes, for me it is clear. I think we aggregate the connections of each node and divide it between the total number of nodes.
Okay, who got that answer, please?
Luis.
Luis.
But
Luis,
-1, maybe?
excuse me?
There are 13 nodes, right?
Okay.
Well, I think, yeah, -1. Yeah, you're right, because we don't count the node doesn't count
Itself.
itself.
And you don't count the node itself, okay?
Okay, okay.
It's 12. Okay. Why it's important to normalize the degree centrality? Why it's more important to have the centralities like this on the right than on the left? Could anyone tell me?
Because you need to take into account the size of the network.
Perfect. Perfect. This account the size of the network. This 1/2, what means this 1/2? This node covers, this node goes to 1/2 of the total nodes of the network. Okay? So we can compare, if I use a normalized degree centrality, I can compare these numbers with the numbers of another network, and I can compare with other network. With this, I cannot. I don't know if it is clear.
Clear for me.
Clear for
No, I don't know how to calculate that normalize. I
You count,
How can I find?
you count the links 1, 2, 3, 4, 5, 6, and divide by how many nodes different from this are in the network. 12. 1, 2, 3, 4, 5, 6, 7, 8,
12.
10, 12.
Yes.
6 divided by 12, it's 1/2. Okay?
Okay.
Okay.
Okay. Thanks.
Let's see this model.
No, it gives you an idea of how many nodes you reach, right, from that node. What proportion of the whole
Exactly.
network you actually reach from that node.
The proportion in the whole network.
Ricardo has a question, a comment.
Okay, please.
You tell us that in some cases the network, the node can be linked by itself, right? So in that cases, the formula change, I guess.
Thank you for the question. This formula works for undirected graphs without loops. Thank you for the observation. But it's very easy to modify the formula or the concept when you have loops, okay? So if I have a loop here, it would be 7 divided by 13, something like that, okay? We are never in this course, we are going to calculate degree centralities of a network with loops, never.
Sorry.
But you can see the formula is very similar, and it's a very good observation. Thank you. Another question?
Yes, sorry, Professor. I don't really get how. I mean, the 112, I don't understand where that comes from, or the 112. I mean, could you please repeat that?
Excuse me? I don't understand.
Yeah, that he didn't quite follow the way you compute perform the computation. So you just divide the number of links or the degree of the node by the total
By the number of total nodes.
or nodes, right? Who was it who asked? Just asked? Who was it? What's your name? The student who just asked?
I was sorry. I don't know if you can understand me now.
Edgar, right?
Yes.
Okay.
Can you hear me?
Yes, yes, yes. We follow you. That you said that you didn't understand how to compute this. So you just
Exactly.
divide the degree of the node by the total number of nodes in the network,
Yes.
right? Is it clear, Edgar?
Oh, okay. I understand. It's the total nodes, not the total nodes that it can reach. Okay, thank you.
Okay.
Okay. I guess we can move on, Professor.
Okay, let's continue. Here we have a NetLogo model where you can see the degrees of the nodes. You can see the normalized degrees. You can color the nodes of this network. This is a very important visual display of a network. Here the network are in colors. When there's a light color, it's little degree. And when there is a dark color, it's greater degree. So you can see here visually, this node is the node with maximum degree, this have less degree, and this type of visual color representation of a network is very important. It's very important, okay? We can visualize also by size, okay? If you have a big network, it's very useful to visualize by color or by size the degree centrality. And the proportion of the sizes indicates which node had more degree and less degree. It's clear, okay? It's very useful when you have big networks. Okay, not so big, but 100 nodes, something like that. If we have 1 million nodes, impossible to visualize. It's clear? Okay. Closeness centrality. Closeness centrality. A very important measure and very easy to understand. This centrality refers to geographic center of a network. A node has a high closeness centrality if the node is near to the rest of the nodes of the network. Okay? Never is far from the action. It's central in terms of geography. It is calculated using shortest paths. Okay? There's a related measure that is farness centrality and closeness centrality. Farness, how you calculate farness from the centrality farness in a network. You calculate the mean distance of the node to the other nodes. We are going to see examples. And the closeness is the inverse of the farness. Okay? Here are the formulas. I'm not going to explain the formulas. I'm going to show examples. Okay? Look this network. We are going to visualize it here in the model. And we are going there to calculate the closeness centrality of this red node. Okay? Let me see if I can. Okay. Let me see one moment. Excuse me one moment. Okay, for example, I have this node, this red node, okay? Yes? The distance from this node to this is 1. From this node to this is 2. From this node to this is 3. If I sum all these 5 numbers, these 6 numbers that are the distances from this red node to the 6 blue nodes, I obtain the farness. If you sum all these numbers, how much it gives? The sum of these 6 numbers.
We read you.
20.
20, okay? 20. If I divide 20 by 6, 1, 2, 3, 4, 5, 6, 20 divided by 6 is the farness, centrality. And the inverse, 6 divided by 20 is the closeness, centrality. I don't know if it's clear.
Who can give a it's just to reinforce it, like the intuitive explanation or description of the two concepts, farness and closeness? Who can tell it? What it means, the meaning, the intuition behind it.
Are you asking me or the students?
The students, just to make sure that they understood.
Yes, thank you.
Any of the students, the intuition behind the concepts, closeness and farness. Anybody?
How popular or unpopular is the node?
Not exactly popularity.
Well, the number. Oh no.
I don't know if popularity.
I think it's the average distance.
Okay, it's the average distance. Okay, it's the average distance. For example, if these are roads, and I'm going to go to every town from here, more gasoline if I start from here. Look, I'm gonna change the node. If I put here, these are the names of the nodes. This is node 0. So I'm gonna put here 5, 4, 3, 2, 1, 0. Okay? Look, if this is the node, what is the closeness centrality? Here are the distances, 1, 1, 2, 3, 2, and 2. If I sum these 6 numbers, it's not 20, it's less, it's 11, okay? And if I divide it by 6, 11 divided by 6 is the farness centrality. So the closeness centrality is 6 divided by 11. So this node has higher closeness centrality. This means that this node is nearer from the rest of the nodes. It's not apart. It's not entirely, but it's a geographic measure, but also a topological measure.
What about, because I don't know, maybe I think it's important to develop Ricardo's idea regarding like a social network. Well, Alex, like what would the meaning be in that situation? Because yeah, when you talk about distances, is more or less clear, very clear, right? But if you're talking about like a social network, what would be the meaning of that, of those measures?
I guess this measure is not used much in social networks. I have seen very few applications of these measures in social networks. It's more in road networks, in airport networks, in geographic networks, but it is possible. I don't know. It is possible applications in social networks. Degree centrality, a lot of application in social networks. Closeness centrality, I'm not sure. Okay. Okay, any more questions? I think these formulas complicate the concept, so I'm not going to explain it. The concept is very clear. Sometimes the formulas are not good to understand, but you can console them. These centralities are very intuitive, are very clear to calculate. Okay, let's continue. Okay, between the centrality. This is a very important centrality. It's not so easy to understand it in the first place. I think closeness is easier. I'm gonna try to explain it. Okay, this centrality has not to do with distances, has to do more with a node that is, for example, this node. Take, for example, this node. Yes? Imagine that this is a communication networks, and this guy here is sending messages here, or messages here, and here in this network are flowing messages, okay? Yes? Messages from here to here, from here to here, a lot of messages. Yes? This red node has high between centrality because a lot of messages that are circulating in the network pass by this network, by this node, okay? For example, if this node sends a message to this node knows the message because it's had to pass the node. But if this node sends a message to this node, very near, he is not, okay? What percentage of the messages that are sent in this network are captured by this node? That percentage is the betweenness centrality of the node. It's not a precise definition, but I want to ask you if more or less the concept is understood. Okay, let me say what is in the slides. Being in a lot of paths, of shortest paths, makes you important. The shortest path from here to here, from this green node to this green node, pass this node. What percentage? Okay. Intuitively, the message of the network passes through you. A node with high between centrality has the ability to be a bridge between different groups. Look, if these are communities, this node with high between centrality, it's like a communicator, a bridge, a broker. I think the name is broker between these communities. Okay. I think one of the best ways to visualize nodes with higher centrality, high between centrality, are nodes which are in a certain way bridges. Okay. This is like a bridge. It's clear?
Yes, Professor.
Okay. I'm going to talk a little bit about the formula. I am a mathematician, so sometimes I explain formulas. Okay. The between centrality of a node has to do with two quantities. The quantity in the numerator are all the paths, all the short paths that go from any node S to any other node T that go through the node B. Okay? And in the denominator are all the possible paths. All possible paths. If I divide all paths, all possible paths that pass through B, and divide by all possible paths, including what goes through B and what not goes through B, this quotient gives the between centrality. Okay. I think it's time for examples because this is a little abstract. Let me see if I can. Okay, I have a problem with this file. Let me see if okay. This is a perfect model. This is a perfect model for seeing between centrality. This is a small model. I don't know if this link. Okay. I've lost my presentation, so I don't know this presentation very well because it's a little long. Okay. Okay, let's see here. Okay. I'm going to ask you questions. I'm going to calculate, guys, the between centrality of this node. Okay? I'm going to ask you a question. How many paths between the other nodes that are not C pass through this node? It's a number between 1 and 10. Okay, I heard says. Someone is saying says. It's correct. Says. 6. It's clear why there are 6 paths. At the right, 3 nodes. At the left, 2 nodes. 3 times 2, 6.
Fuck. Sí, sí.
What are the 6 paths? From E to A, 1. From D to A2. From F to A3. Okay, and from E to B4. From D to B5. From F to B6. So this node captures 6 paths between nodes of this network. 6. Okay. How many total? How many total paths there are? For example, from E to F is 1. From E to A is another. From D to F, how many there are?
10.
Ricardo is saying 8.
Okay, 10. 10. So what is the between centrality of this node? 6 divided by 10. I don't know if I'm correct. I'm going to put this here. 6. Normalize. Okay. I think here is a mistake. Here is a mistake of the what? Of this model. It's 10 and not 20, okay? It's 10 and not 20. So the centrality of this is not 0.3, but it's 0.6. It's my mistake, okay? This is an old presentation, so I have corrected that, okay? Excuse me for that. It's 6/10. Okay. Guys, the important thing, okay, learning how to calculate these centralities, I guess is fun. It's not difficult, but the important thing, I guess, today is not to calculate it because network X, Gephi, does the calculations. The important thing is to understand in what context these centralities are used and why they are important. Okay? And what is the difference between the different types of centrality? And I'm going to show you examples of that. Okay? So up till now we have degree centrality, closeness centrality, and betweenness centrality. Okay? I don't know if there's question. Okay. I'm going to review this clustering coefficient is not strictly is not a centrality measure, but I'm going to put it here because it's very important, and each day is more and more important. You remember that? You remember this graphic, okay? We saw it last session of clustering. Okay? It's a very important measure. It's not the centrality, but I put it here to so you don't forget that this is a very important measure of okay? The last one that I'm going to show you, is eigenvector centrality. Okay? This centrality is very important. Is okay. It's a refinement. It's an improvement of degree centrality. It's an improvement of degree centrality. What I'm saying here, degree centrality is a little myopic. Why? Because degree centrality ignores the place that a node had in the network. It's clear that you count only the links, but you don't know if the node is at the left, at the right, or if the neighbors are important or not important. Degree centrality only looks the links of the node and not more. That's why I say that it's a little myopic, I guess is the word. For example, what happens if a node is adjacent to other nodes that are important? If a node is adjacent to other nodes that are important, this node becomes important. Yes? For example, if you have famous friends, you are important because your importance increase if you have famous or popular friends. It is possible that you are not popular, but you have a lot of friends that are popular. That makes you not popular. That not makes you popular, okay? Not, but that gives you power, okay? Because if you want to do something and you have popular friends, you can tell to your popular friends, please help me. I need to do a job or something like that. I don't know if this is clear. Okay. If there are no questions, I continue. Let's see a small example. I think, okay, let me reduce this a little bit more. Okay. Okay. me. Wait a minute. Okay, here is a node. What is the degree of this node? 2, okay? It's okay? Are you listening to me?
Yes, 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 yes.
Yes, Profe.
Yes, it's okay.
Okay, this has degree 2. Not very good degree, but look the neighbors. This degree 6. This degree 7, I guess. This is not popular, but their friends are popular. So this gives power to this, okay? Let's see. Okay, this is a girl. This is a girl. It's called Nancy. This is Nancy. Okay, here it is, Nancy. And we are going to see Warren. Where is Warren? Warren is here. Oh, excuse me. Warren is here. Okay. Degree of Warren, the same degree of Nancy. Okay. But these neighbors have low degree. So this node has not much power because his neighbors are not powerful. Okay. Let's move. Okay. Okay. Here are the eigenvector centralities of these nodes. I have not explained yet how they are calculated. It's a mathematical concept about eigenvectors. It's not difficult, but okay. What I want to tell you is that the measure eigenvector centrality of this is 0.23, and of this is nearly 3 times as much, 0.62. Degree centrality, the same, but eigenvector centrality, very different. Why? Because we are not myopic. Eigenvector centrality sees not only the degree, but also the degree of the neighbors. And of the neighbors of the neighbors. It's a recursive definition. Okay, I don't know if there is questions. I have not explained how to calculate these numbers. Okay, I have not explained. But please tell me if the concept is clear. Please.
Yes, pretty clear. I guess it is calculated using the eigenvectors of the adjacency matrix.
Excuse me? Could you repeat the question? Excuse me.
No, it's a comment. I guess it is calculated with the eigenvectors of the adjacency matrix. I guess.
Yes, with the principal eigenvector of the adjacency matrix. But there's an easier way to calculate it. I had I had the model this morning and okay. But let me okay. It's easy to calculate. Let me show you. I'm gonna try to find a model that calculates the centrality. I'm gonna try because let me try. Let me 1 second. Okay, let me try to find this model. I have problem with Dropbox. I don't know what happened. Okay. Okay. I'm not sure. Oh, I guess this is. Oh, I'm very fortunate, guys. I think this is the model. Okay. Okay. Okay, guys, I'm gonna run this model, and you are going to tell me what is happening. Okay, I'm not gonna say nothing now. I'm going to run slowly the model, and you are going to try to guess what is happening to this network. It's clear? Yes? Okay.
Yes.
I'm
Yes,
going to
Professor.
begin. I'm going to begin slowly. Look. Can anyone tell me what is happening? It's a super important concept in network science. What is happening to the network? Please. It's not clear. I guess it's not clear. And I guess it's not easy, but perhaps some of you could try a guess.
Could you try again,
Yeah,
please?
I'm gonna try again. Look. Look, look this red note and look the numbers.
I believe it's like random walking through the
Exactly.
network and
Exactly.
counting every time it passes through a node.
Exactly. I guess you could guess it looking here up. Okay, it's a mistake, but it's random walk. I'm gonna do it. Okay. Random walk. Beautiful. It's a robot. It's a robot. And what are these numbers in the notes? 215. What are these numbers? Please.
That's the times the red node has passed over that node.
Exactly. The number of visits to the node. Okay? Okay? If you divide these numbers, if you put, what is the maximum number here? I guess it's 218. Yes? Okay? If you divide all the numbers by 280, you obtain here 1, and in the rest, a number less than 1. Okay? Yes? It's correct? Because this is the
Yes.
maximum. Guess what? These numbers, for example, 250 divided by 280 is the eigenvector centrality. It's an approximation of the eigenvector centrality of this node. So, if you do a lot, look, 1,072 movements of this red node, but let's do more, okay? 200, 2,000, let's put it, okay? 100,000, 150,000, okay? If you capture the maximum number of these and divide all the numbers, you obtain a better approximation to the eigenvector centrality. If you do a random walk with a lot of movements, in the limit, when this is very big, you get what? The eigenvector centrality of the nodes. It's a very beautiful, okay, it's a very simple way to do it. It's a very important way to do it. Today, random walks, for example, when Dr. Fabio Gonzalez is going to be here in the course talking about machine learning for graphs, I'm sure that he's going to talk about random walks. because random walks are very important. There are a lot of type of random walks. This is a very simple random walk, okay? This is one way to calculate the eigenvector centrality, and it gives an approximation. But if you want the exact value of the eigenvector centralities, it's easy also. You, as Luis Fernando said, I guess, the adjacency matrix of the network, and you calculate the eigenvector of the matrix who has the greater eigenvalue. Okay, that's not important. It's very easy to calculate. Okay? I don't know if there is questions.
Yeah, maybe I have a question. I am just wondering if there is like a metric that represents the importance of a node in regard of how many paths are only connected by that node. In one of the examples that we saw before, one metric like this could help giving an understanding of how important is one node. But for example, if a specific node connects two parts of a network and only that node connects those parts, that's a very important node because yes, communication would be disrupted if there isn't. So is there a metric to measure that?
Yes, between the centrality.
But it doesn't.
Okay. There's okay. Okay. Between the centrality normally are bridges of a network. If you remove a node with high between the centrality of a network,
There is a higher chance
you could disconnect the
was
network.
a bridge.
You could disconnect the network, but
Yeah,
it's not. But not
yeah,
always. Not always.
yeah.
Not always. Not. It is possible to have the node with highest between the centrality, and when you remove it, you don't disconnect the network. It's not. It's probable, but it's not sure.
Exactly, not always. So I was wondering if there was a metric.
Okay, there's a concept in electrical engineering or in some areas. There's the notion of minimum cuts of a network of nodes that disconnect the network in, I guess, in Kirchhoff laws and all that. And it is a concept that could be used in network science. Okay, we are talking about four important centrality measures. But let me tell you that today there are about 15 centrality measures. Okay, the most popular are these four. There's for example, there are measures, there are extensions of these eigenvector centralities. There is a measure called diffusion centrality. So there are it's a field that is very researched. In this course, we're gonna talk mostly of these four. But I invite you to consult in the internet that there are others. It is possible that in the articles that you have read for your mini project, it is possible that you have found other centrality measures apart from these four. For example, there's one called CATS. CATS with K, no, not gatos, but CATS, K-A-T-S, CAT centrality. That is, it's a centrality measure, very sophisticated, and is important. So this is an open area. Okay, it's an open area. I don't know if there are more questions. Okay. Let me go to the web page because I'm gonna show you. Are you seeing the web page? Yes?
Yes, Profe.
Okay, look. Uh, in this week free centrality measures, there are two videos that I highly recommend. Andrew Beveridge, it's a network scientist who publishes fantastic videos explaining network science concepts. And I recommend you this video is 15 minutes. 15 minutes. He explained in 15 minutes much better than me, sincerely, the basic centrality measures with spectacular examples, and I guess it's very clear. Okay? Here in this video, algebraic centrality measures, okay, in this he explained degree, closeness, and betweenness, and in this he explains eigenvector. He spends 11 minutes because he explains very clearly how to calculate that, okay? So I highly recommend, and the advantage of this is that you could see this video 10 times, 15 times. I have seen these two videos a lot of times. Much of my explanation of these measures come from these videos, okay? Okay? Okay. Let me talk a little bit about this process, okay? A little bit about this process. This random walk. Because this random walk historically is very important. I don't know if any one of you knows this measure approximates to eigenvector centrality, but is called, but has a special name, a very famous name. I don't know if
Monte
any one
Carlo.
of you knows.
It's Monte Carlo.
It's not Monte Carlo.
No?
I guess. Okay. The two young people discovered this random walk and invented a famous algorithm, one of the most famous algorithms in history. I don't know if you know what persons I am talking about and how it's called the algorithm. No? Okay, I give you hints. The two persons that discover this algorithm and these random walks are the founders of Google. So I guess that you now could guess what is the name of this process.
PageRank?
PageRank. PageRank. This is the basis of PageRank. If this is internet, if these nodes are nodes of the internet, okay? Okay, one important thing. Internet is not an undirected network. Internet is a directed network. So here, I'm not being exact. Here, you could go from here to here and from here to here because it's undirected. In internet, it's not. This random walk was constructed for directed networks, okay? And the first approximation of the famous algorithm that is called PageRank was with directed networks. It's a little more sophisticated than this, because if the network is disconnected or there are problems, this is an ideal network where the random walk is not going to fail. But if it is a directed network, it's possible that you go here, and this is a sink. Remember, a sink. So from here you could not go anywhere. What they invented that if you are doing the random walk and you go and you arrive to a sink node, a sink where you can go out, you jump, jump here and continue. So these two persons do a modification. They publish an article, and after publishing the article, I guess you know the story, they founded a company called Google. And this was the base. The PageRank algorithm was the principal motivation for them to begin his enterprise called Google, okay? This PageRank algorithm, this PageRank centrality measure is very used, is very popular, and is very important, but in directed networks, okay? In this course, we are not going to talk a lot about directed networks. Okay. I don't know if there are more questions. Okay. I'm going to invite you to a workshop. I'm going to send by the chat a document of about 3 or 4 pages. Let me show you the document. I guess I have it here. Here. Okay. Okay. Are you seeing this document?
Yes.
Okay, guys, this is a document from a book, from an excellent book about social networks. In this book, the 3 authors of the book show an example. This is an example. Let us have a look at an example network of people who work together to see the importance of each of these measures. What are each of these measures? The 4 centrality measures. Look. I'm going to reduce a little bit. This is the network that they studied. It's a real network from an enterprise, from an empresa. These are the names. Here is the adjacency matrix. And in 3 or 4 pages, they explain, and with a little bit of numbers, but you know what each of these 4, okay, okay. I invite you to not see this boundary spanner, okay, this column out. Only eigenvector, closeness, betweenness, and degree, okay? For me, this is the best explanation of the 4-degree centralities. In context, in a real example, and I invite you, I'm going to send you by the chat this document, and we are going to have, I don't know how much time, I guess 20 or 25 minutes. It's 7 and 10. Let's put 25 minutes for you to read this and try to understand. In final, there is a summary. There are 3 or 4 pages. And when we return in 7:35, we are going to discuss or if there are questions about this document, we are going to answer them. And I think it's one of the best ways to understand these four centralities. Okay? Yes? So I'm gonna copy. I don't know, I'm not very expert in Google Meet, but I'm going to try to send you by the chat. I am here. Where is the chat? Here's the chat. I guess I'm gonna put here case study centralities. Okay. And I guess if I paste, oh, paste. Okay. Okay, I don't know how to send you this document. Luis Fernando, help me.
You could
I
use
think
Google
it's-
Drive.
Yeah, maybe via Google Drive would be better.
Oh, no, I don't know how to use Google Drive. I don't know how to use
If you wish,
Or maybe through the classroom.
yeah,
Or
maybe,
maybe an email.
you
I
can
don't know.
mail it to me, and then I can share it via Google Drive if you wish.
How? Thank you. I'm gonna send Luis Fernando the document. He's going to put it in Google Drive. Okay. Let me do that. So I'm gonna here is Outlook. I guess by WhatsApp is easier. Let me.
Yeah, that would do too.
Okay, thank you, Luis Fernando. I'm going to Luis Fernando. Okay. I guess here works the paste. Okay, I'm gonna listo. I'm going to the desktop. Where have I this? Local case study.
Yeah, WhatsApp would do. And then
Okay.
just drag and drop.
Okay. I have sent Luis Fernando the document. He's going to send to you the document. And I guess, okay.
Just give me a second.
And when all of you, I am going to wait until all of you have the document and are visualizing the document. And in this moment, I'm going to stop talking and I'm going to give you 25 minutes to read the document, okay?
Okay.
Okay, so I'm almost there. Hang on. Guess we're there. Please let me know if I'm going to share a link, and just let me know if you can access it. So I just shared the link. Let me know if you can see the file there, paper. Professor, though it's 7:15, so let's say we usually take a break at 7:25, so that will be 10 minutes. So maybe
the break is okay.
So
okay. We are going to do okay. Let's talk about the mini project.
Sorry, Ricardo has a question. Ricardo?
Sorry, yes, I was thinking about what you say about Google and the algorithm, and yes. I have no idea what has to be one thing with the foundation of Google, but it interested me. So maybe you have some video that explain it, that share it maybe.
Are you talking about PageRank?
Ricardo.
Yes,
I have a lot of information. It's one of my favorite things. in my classes here in Escuela Colombiana de Ingeniería, in linear classes, linear algebra, I talk about, I dedicate one class it's, I'm gonna put in the web page.
Thank you, thank you.
Links to videos and to okay, I'm gonna put the original. I'm gonna put you, if you are interested in the original paper that Larry Page and Sergey Brin, founders of Google, wrote. It's a wonderful, wonderful article. So,
But
I'm gonna
you're
put.
saying what has to do with Google? That's very weird.
Okay, so
for me.
yeah, it's just to rank the pages, the web pages, when they use it as a basis for the Google search, right? Maybe you could develop a little bit on that, Professor.
Yes. Okay, let me 3 or 4 minutes because this is very important. Before Google, there were Yahoo. There were a lot of sites that search information. But listen to me. When someone make a query searching information, that information was received by Yahoo. And guess an impossible thing, unthinkable today. Humans were responsible for analyzing the query of the person who consulted. Yahoo had a lot of experts, I guess 50 experts, that they say, okay, where is that information in the internet? We're going to send back to the person who asked, and it was done by humans, okay? Humans. Larry Page and Sergey Brin had a crazy idea. Look, listen to that crazy idea. I guess that the same internet could answer the question of the users. And everybody tell to Larry Page and Sergey Brin, are you crazy? How are you gonna do that? The same internet answers the queries and do the ranking. It's impossible. This is done by humans. Humans know the information. And they insist in that, publish PageRank, and the history of the buscadores was broken in 2 parts. That's a lot of things to say about that, but for now, I think that's okay. Okay, Luis Fernando, I guess
It's 7:20.
Okay, we're going to do the following. In the 5 minutes before break, we could talk about the mini projects. Yes?
Yes,
Fernando.
please.
And when we go after the break, we join a little bit for certifying that you have the document and do the workshop after the break. Okay? Okay.
Yeah, maybe let me just share the screen.
Okay.
So just to have the assignment handy. Okay, let me just do that. I'm not share the whole screen. And I'm just gonna share this. So we posted the assignment to submit the final report of your mini project. So have you gone over it? We emailed you that. So remember, this is the small project. So it's just about like trying to reproduce the results of the paper. And as we discussed, like, when was it, last time maybe? Maybe it could be impossible to reproduce the whole thing like in this short period of time. So do your best to try to get as much as possible, okay? To try to. So there are some indications, some instructions about that. So you need to present a report, which is like a paper and there are here you see the sections that this paper should include, like just a summary of what the project is about, or the case study that your project, mining project is based on, then describe data set. And here, by the way, there are, I don't know if Professor, maybe you could develop a little bit about this, like there is a summary because some of these things we haven't quite gone over them yet, but today we are talking about the centrality algorithms, right?
Yes, yes.
So there are several problems, and of course, in the papers, you may address some of these problems, but maybe some of them, maybe a couple of them, maybe all of them, but or maybe usually I think you might just address one or two of those problems, right, Professor?
Yes, in the majority of articles that you find in the internet about network science, research articles, you found these topics: centrality, pathfinding, community detection. The most popular, I guess, is community detection. Nearly 70% of research articles have to be with communities. It's a very popular. So this is very common to find. If you don't find, if you find none of this, it doesn't matter. It's possible that you have an article that doesn't mention node embedding or centrality, or it's possible. It is not, it doesn't matter. But these are guidelines for you, for that you know that these are important things, and you find them. It's very good that in the video that you're gonna make, emphasize a little bit about these aspects, because these algorithms are important and these concepts are important. It's for guidance for you, but it's not this is not enforced. It's because you could find an article that doesn't mention any of this, I guess.
And this is what I'm highlighting is very important, right? So don't start from scratch to implement the algorithms, but rather try to find the software tools as Professor has shown in all his lectures, and just go and use them, right? So just apply them. Try to select the proper tools, software tools, and just apply them to analyze your particular network. Okay, is that clear? Because we don't have much time, and then there are software tools there to do this.
Okay, let me a small observation, please, Fernando.
Of course.
I know that there are a lot of students that are systems engineers. So it's very good if you could implement some algorithm because you are expert in that, and it's a bonus. But the majority of algorithms that have the research articles are implemented in NetworkX or in Gephi. So it's not necessary to implement them. You can modify them or not modify them. It's up to you. If you are very fond of programming and of algorithm analysis and something like that, but here are economists and are biologists, so they are not going to do that. So it's important that you. Okay, the most important thing for these mini projects is that you use the tools, NetworkX, Gephi, and get fond of the tools, and read the research article, try to implement some of the things that are in the article using the tools. This is the main objective of this mini project.
Also, I think it's also important, and I think we need to stop with this before the break. Since there are so many of you in the class and so many teams, then we rather ask you to prepare an explicative video before the session, and then we can maybe proceed faster, and then we can leave the videos available for everyone there, so that way we can gain some time here in the session, in the class, and then focus maybe on some of the results or something like that, right? So you rather prepare a video explaining the results of your project, and then you still need to submit the written report, and we'll have discussion in class regarding the results of your project, okay? Your many projects, small projects. And something similar but I think we can talk about that later. Applies for the progress report of your term project. Okay, so I guess we can stop now, and then we'll have a 15-minute break, right, Professor?
Okay, perfect.
Okay, so we'll see
So
you at 7:40.
7:40, we are back.
We're
Thank
back.
you, Luis Fernando.
Thank you. Professor, are you there? I'm sorry, we ignore you, Alex.
Hello.
I think Alex had a question because you asked them to you told them to read to the workshop, and then so I don't know if this is time for them. You're gonna give them a few minutes to read the paper, and then we'll take over. So you can read on the.
One moment. Okay. Is a question from Alex?
Yes, it's because they are expected to read the paper in 15. You said like 15 minutes, so I don't know. Maybe we'll meet in 15 minutes, or are you gonna
I guess more time. I guess more time. I guess
in 15 minutes, right?
25 minutes. 25 minutes or 20 minutes. At 8. At 8. 8
At 8.
o'clock.
So
At
let's
8.
meet at 8, and then you will read on your own the paper, right?
Okay. Everybody has access to the paper.
Just let's make sure of that. Is it clear? So
Okay.
we'll meet in 20 at 8 p.m. Okay, and
There's-
meanwhile you read the paper. Okay,
Okay. You're gonna read the paper, and at 8 o'clock, questions, and we talk about this reading. Okay. Okay.
Sorry, Professor, where's the material? On the email or last one? Where can we find it?
Professor, it's 8. So are we back? Hello? Professor, are you there?
Hello?
Okay, so it's time to continue.
Okay. I don't know if there are observations or questions about the reading. I think it's a very clear explanation of the four important centralities, the interplay between them. When a node has both degree centrality and between the centrality, there's a lot of power. I think it's a very good example. If you notice, the author begins with one network and makes a modification, adds a link, and when he adds a link between Fred and David, I guess, the network is different. The centralities change. I think this reading is important to do it several times. Only today we are aware of this centrality, so it is not easy to grasp them. But it's important that you could understand conceptually the centralities. Very, very important. Okay, I don't know if there are questions. If not, we can continue with. Okay, let's continue. Let's continue with the presentation. I'm gonna show you. I want to show you first. Okay, I'm gonna share the screen first. I'm gonna show you a NetworkX Jupyter notebook, a very good, a very important Jupyter notebook. It's in the web page. Are you seeing my screen?
Yes, Prof.
Yes.
Okay,
Yes.
Thank you. Okay, this is a NetworkX Jupyter notebook. The title is Centrality Measures in Network Science. Author is it's a girl. It's a girl. It's a woman who works in Philippines. It has very good NetworkX Jupyter notebooks. We're going to see several. Okay, look. You can download this. You can download this Jupyter notebook from web page. It begins with a description, a very short description of the four centralities. And here it's a little code. Here she introduced the library NetworkX, and for drawing matplotlib. This is code for reading a network and for displaying it. What I want to show you here is the following. I'm gonna reduce a little bit this. Okay. A little bit more. A little bit more. Oh no. It's a little bit difficult. Let me see. Okay, let me see a little bigger. Okay. This is a fictitious network, a small network. Here we have degree centrality in colors, and we could see this is the node with the more degree centrality. Simultaneously, we could see the closeness centrality, and we could see, for example, that this node also has high closeness centrality. This node has high degree, and it's also in the center of the network. The distances are not are not big from this node. Here we have the between centrality. Here we have the eigenvector centrality. Seeing simultaneously these four networks is very important because you can compare visually and immediately the different centralities. You can change here. You can change the network. This is the dolphin. I don't know if you remember this. No, excuse me. This is not the dolphins. This is another network, but you can change here the network and visualize another network, execute the code, and you can use this Jupyter notebook for visualizing simultaneously the centralities. It's a very important tool for visualizing the centralities. Here, Erika Legara is showing, this is a famous example. It's in the web page. Let me show you where this is. If you go to the web page, in the part of here, okay, here are 3 case studies that are similar to the one you just have read. Okay, the one you just have read analyzes a network of researchers. Yes, of researchers. Here it's a video of Andrew Beveridge, Centrality in the Dolphin Networks. In 3 minutes, Andrew Beveridge explains the different centralities in the Dolphin Network. A very good explanation. Okay. This here is a zip file of another network, famous network that was analyzed, is the Medici family. I don't know if you are aware of the Medici family. Could any one of you tell me what is the Medici family? We have it here. This is a network, and here is the Medici. I don't know if any one of you know anything about these families. Yes? No? Okay. I'm going to tell you very, very briefly. This is from 16th century in Florence, okay, in Florence. Italy was the most important country in the world in that moment because of commerce. The origin of banking began here, and this family, Medici, got a lot of power. Medici was a family who had not much money, but the Medici, the woman from Medici married men from those other families and began to acquire money. And in 1 century, approximately, Medici, the family Medici, controls all Florence and was the center of the world. This is an important historic moment. And in 1993, two sociologists investigate why there was power in this family and wrote an article, a famous article that is here. The article is a little bit longer than the one you have just read, but this is a very interesting article where you could see again how the centrality measures are important. Okay? This other case study we're going to talk a little bit later when we see global measures. Okay. He talked about another. Okay, here is the network. Here are the centralities of this. It's a very small network, okay, but it's a classic network. Is the eigenvector centrality, etc. Okay, the karate club. I have not talked about the karate club a lot, nearly nothing, but I guess it's the most famous network in network science. I invite you to investigate about this. This network. Look, this network is a network of university students who are in a club of learning karate. It's okay, and okay. This is a very good Jupyter notebook. I invite you to explore this Jupyter notebook. It's in the It's in the web page. Let me tell you where is. Where is? Lee, look. Oh no. This. Erika Legara, week 3, centrality measures. This link, it's this file, okay? Okay. Let me show you this model because it's very important. Okay, this model looks a little bit complicated, too much buttons, okay, but I'm going to try to explain here. And a very important application of the centrality measures. Let me display here a network. Okay, this is a relatively big network. It's displayed in a circular layout. Okay, but let me display it in the spring layout. Okay, it's a network. It's a network model. It's a preferential network. We're going to talk about network models. I guess the next session. For now, let me tell you that the preferential network, one of the important features of a preferential network, is the existence of hubs. You read in the reading you read, you saw the word hub. This is a hub, okay? Let me, excuse me. This is a hub. Look. What is a hub? It's a node with degree centrality very, very, very big. Very big compared to the others. There are a lot of real networks that have hubs. This is a hub. Okay. Okay. We are going to diffuse information in this network. Let me tell you how. Here, this slider, it's telling me how many people are going to acquire the information at the beginning. For example, 2 persons. 3 persons. If I click here, look what happens. 1, 2, 3. Let me put this here. 1, 2, 3 persons have an information, and they want to spread the information, okay, in the network. Or could be these 3 persons are sick, and the sickness of these 3 people is going to spread in the network. So we could have we could be talking about diffusion of news, of gossip, of information, or diffusion of disease. Okay? I don't know if it is clear. Okay. We are going to diffuse the information. So I'm going to click, excuse me. Here. Okay. I diffuse information. Here is the curve of diffusion that it has. I think you know that has this shape. It's a logistic shape. And here are here is another graph that has this peak, and this is every day. If every tick, let me show you here. I'm gonna put the network again. I'm gonna do it slowly. Initially, there are 3, and in each step, okay, the diffusion. This is the total number of red nodes infected or that have the information. And this is every day. Each click is 1 day. Yes. One day there were 4 infected, other day there were 6. The next day there were, I don't know, 8. The next day, okay, this is a peak. Very important in COVID, no? It's a peak. From now on, this is descending. This is the maximum number of infected in 1 month, for example. But this is cumulative and is always increasing because it's the total number, okay? I don't know if there are questions about this.
I'm a little curious.
Yes.
I'd like to do an experiment on this model. I see that you can select any of those nodes. For example, the hub that you showed before.
Yes.
How would be the curve in that case? Only in that for that person.
What is your name, please?
Leonardo. Well, my name is Edgar.
Edgardo?
Leonardo.
Leonardo, thank you for the question. You anticipate my thoughts. I was going to talk about that. Thank you. What we have just done was choosing randomly the free initial persons in a random manner. And when I choose in a random manner, this is the way, the evolution of the infection, okay? Now I'm gonna change the way we infect the initial people, and we are going to infect the hubs. And we are going to see the effect, how this curve changes when I began with the hubs. It's clear? Let me try it. I had another model, but okay. Let me try it. Okay. I'm going to put the network again. This time, I'm gonna use the mouse to infect. Entonces, here, I can infect, I'm going to infect three, but this, okay? I guess this, and I guess this, okay? We are gonna see the diffusion. Okay, look, 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 look. It's very important. In one day, a lot, a lot. In one day. Why? Obviously, because this is high degree. Let me continue the diffusion. Different, okay? Different. Let me see if I can put simultaneously this infection with hops and the random. Let me wait a minute. Let me think a little bit. Okay. Okay. Here is the network again, but this don't disappear. I am in the right path. I'm gonna infect this. Again. Here, random. Oh, fine. I could do it. There's a difference, a very important difference in the graphics. For example, from this point to this point, there are 3 or 4 days. This indicates me that when I have hops, the infection lasts fewer time than when I do not have hops. And this is important. Time is very important in COVID and in infection, time. And look the daily infections. In the red, there's a big peak here. Here, the peaks are not. Okay? Okay. I don't know if there are questions.
Excuse me, sir. I have a question.
Yes.
Well, regarding our mini project, which is about spreading misinformation on social networks,
Yes.
could we use this kind of model to implement that paper?
Yes.
Because
Yes.
it, for example, it not only has misinformation, because it only has positive notes as
Okay.
positive seeds. Could it be possible to do it with NetLogo?
Okay. Okay. It's a very good question. First, this model it's in the web page. You could download it and you could play with it. I call these models laboratories. Okay, they are not complete laboratories, but here you can play and you can see qualitatively. Here there are no numbers, but after you experiment here, you could go to numbers. Okay, you could be how many days are here, etc. in NetworkX. But this is very important because you could play with this. Okay, it's not difficult to do it in NetLogo. NetLogo is a very easy to program language. It's very intuitive. Besides, we have the ChatGPT. I have made about 10 questions of NetLogo to ChatGPT, of questions that I am investigating, and ChatGPT brings the code and all that, and ChatGPT had saved me a lot of time in one or two things that I am doing. I guess you know that this ChatGPT is changing the way programming and a lot of other things. Okay, you can email me if you need. I have a lot of models like this. This is a very complicated model, but I have more simple, and you can email me if you want to. I could give you some of these models for that you can play with them. Okay.
Okay, thanks a lot.
Okay, let me show you another important thing in this same laboratory. I'm gonna set up disappear graphics. I'm not going to diffuse information now, but I'm gonna do other important thing that is attack. Attack. I'm going to attack this network. Okay? Here is the percentage of attack. 10% I'm going to eliminate from this network 10% 10% of the nodes. Okay? Look. These are the nodes that are going to eliminate. If I click here, the node disappear. And there's a new network. Okay? This attack was a random attack. Let's see if I now want to diffuse information, how the information is diffused. I guess I'm going to put here again the nodes, and I'm going to diffuse. Okay, I guess because they were attacked, this graphic is like that. And look, it's not reaching the peak. Because why this curve, please tell me you, why this curve does not reach the peak here up? Could you tell me that? Why?
Because there are
No.
Disconnected network.
Okay, you are experts in network science. Experts. This is disconnected. Let me show you better the disconnection. I'm gonna try. Look. Disconnected, disconnected, disconnected. Okay? Okay. This is called a random attack, or also a failure. When you have a power grid of electricity in a country, and there's a failure, you don't know if the failure is going to be in Bogota or in Cali or in Medellin. It's a kind of random failure. Okay, it's a failure. But it's very different if a terrorist group is going to attack the oleoductos, because it's possible that they are thinking in attacking the nodes of the oleoduct that are more important, more degree. Okay, it's a deliberate attack. So we are going to here to develop a deliberate attack. Let me see. Okay, again the same. I'm using the same network. Here are the three important models, but I am using this. Here is small world, but later on we'll talk about that. Okay, here when I use the mouse. I guess I can't use the mouse for an attack. No, here, mouse attack. So I can do that. Oh, this. Excuse me. Oh, this node. Excuse me. excuse me. Again. I'm gonna choose further nodes. So look what I'm going to do. I'm going to, no, this is activated, excuse me. This is also, okay, patience, please, patience. Okay, it's not activated, so I can move it. Let's choose the hubs. Here is one, excuse me, this is activated. This is one hub, I'm gonna put it here. I don't know if this is another hub. I'm gonna put it here. And I'm gonna, this is another hub, I guess. I'm gonna put them here. And now, okay, I'm going to attack, delivery attack. I'm gonna attack this, go, this, go, this, go. Observe that before I was attacking 10 places and here only 3. And notes here, diffusion. Okay. Different. Let me see. Okay, the network is all connected. Okay. Infinite possibilities. Infinite possibilities here to play. I have a more complete model where you have not only these free network models, but the dolphins, all the important, the classic networks, and you can load it here and play with that and understand. Okay, I have another, okay, look, type of attack. What is degree? What is degree type of attack? Hubs. Betweenness. I'm going to attack what here in betweenness? The bridges, the brokers. And here random. So I have 3 types of attacks and I can analyze. Okay. In NetLogo, after visualizing and playing a little bit, I can do experiments. I'm going to show you a little bit. I use a lot NetLogo, but I think it's not the best tool for network science, but I use it a lot. Here we have different parameters, and we can here do an experiment, decides which values for example, initial nodes from 1 to 10, diffusion from 10 to no sé qué, to I don't know. And then you put OK, run the experiment, and it generates an Excel file, a very big Excel file that you could bring to Matplotlib, ggplot. Do you know ggplot, guys?
Yes, Professor.
Yes.
I want to ask a question because it's important for me, and I'm gonna see the Google Meet. Excuse me. Okay, I want to raise the hand. The persons that use a graphic library, a spectacular graphic library called ggplot, ggplot. It was developed. Okay, not much hands, but okay. How many hands? 3? Okay. It's a library that was developed for R language, not for Python, but there's an equivalent library for doing graphics it's called, I don't remember the name. Well, I don't remember the name. But it's a very powerful library for doing graphics for data science. And you can do the experiment in NetLogo, go to Excel, read the Excel file in ggplot, and do all the quantitative analysis that here are quantitative. This is one way, is the way I use most. But I guess you know a lot more of that, of data science, of graphics library, of visualization than me. So I guess you have the appropriate tools that you use. I only want to tell you, and I guess I'm not I'm not a real expert in data science. I know about network science, and I guess there are better tools for doing that. Okay. I don't know if there are more questions. Okay. Let's close this model. I guess it's not enough. It's not enough, but I guess it's a good introduction to centrality measures, to local measures. Let me, in the 15 minutes or so that I have, introduce you to global measures. A network has local measures and has global measures. And it's important that you know also the global measures. So I have a presentation that I want to show you. Okay. Let me show you first. I'm going to do the opposite that I did in local measures. I define the measures and then I show examples. Here, I'm going to show the examples, and if there is time, I'm going to go to the definitions. Okay. I guess oh, fine. As you guess, another logo model. Okay. Okay. Here we have a lot of networks. I want that one of you, if you are saying, tell me which of these networks you want me to load. Any one of you tell me which of these. If not, I choose one.
Yes.
Oh, oh. Okay, yes, I'm gonna try. It's the biggest network, and NetLogo is very slow, but I'm going to try. If it's not function, I choose another. Sorry. Okay. Look. This is the protein network. Remember? Of this case study of the first week. And I guess I'm going to have problems here. Okay. Okay. I guess I have to change of network, sorry. Okay. Okay, I'm going to choose the network, sorry. I'm going to choose karate. Okay, these are the nodes. Here is information, 34 nodes, 34 dots, 78 links. Where are the links? Here. This is karate. Okay. Let's start with global measures. Let's start with the most important global measures that you know. Let me reduce. Okay. Here, guys, please, very important. Here at the bottom are the three most important global measures. I guess the first one, degree distribution. This is the degree distribution of the karate network. It's normal, Poisson, okay, it's a particular distribution. Here, it is very important, average path length, small world, average path length, 2.4. This number is very, very, very important. And this also, clustering, 0.5, communities, triangles, lot of triangles, communities. Global clustering, global, guys, global clustering 0.5, it's a very high global clustering. Okay, it's a small network, and it's very, and had a lot of links, and had a lot of triangles. These three, clustering, degree distribution, and path length, the three more important measures of a network. I guess in every research article, there you talk about clustering, degree distribution, or average path length. Okay? Okay. Let's look here. Diameter, 5. What do you think is the diameter of a network? I invite you to propose a definition. You know the diameter of a circle, obviously, but the diameter of a network, what is the diameter of a network? What do you think is the diameter of a network?
The longest path?
Okay, the longest path. Here in this network are two nodes that have the longest path, 5. This is the diameter. Okay. Radius is a little bit more difficult to define, but first I'm going to define another concept. Okay, density, 0.1, okay. Low density, we have talked about that, guys. Networks are sparse. Networks are sparse. Densities of more than 0.2 or 0.25 are very rare. And if a network is big, the density, more bigger a network, less the density. Okay? It's a global measure. Okay, here is the maximum degree, 17. Eccentricity. Let's talk about eccentricity. I'm gonna show here. Look. It's an important measure. I like this measure, eccentricity. What are these numbers? Why this is eccentricity free? Why this is eccentricity 5? I invite you to propose a definition of eccentricity. Anyone? No?
No, it's really difficult.
Okay, it's not so easy. I'm going to tell you if you understand me. Why the eccentricity of this node is free? You calculate all the shortest paths from this node to the rest of the nodes. Okay? And the biggest shortest path is the eccentricity. Clear? All shortest path from here. The biggest shortest path from this node to the rest of the node is the eccentricity. Okay? And what is the radius?
It's not the smallest.
No.
Shortest
No,
path?
look. From this node to this node, from this node to this node, what is the shortest path? 1. So it would be always 1. Okay? If it's the smallest, the eccentricity of all nodes is 1. It's clear? Something like that. Is the biggest. Okay. When I read the definition, I ask the same question. Is not the smallest? No, it's the biggest. The minimum eccentricity is free here in this network. Okay, there are 1, 2, 3, 4 nodes that have eccentricity free. This common minimum eccentricity is called the radius. I impart a class in my university, and I 2 or 3 weeks ago was explaining diameter and radius, and a student made an interesting observation. It was a girl. She told me, oh, that can't be because the diameter is always double the radius. So if the radius is free, the diameter had to be 6. Okay? What I tell to the student, okay, the diameter, if radius is 3, diameter is 6 in geometry, but in topology, in network, it's a different thing, okay?
Okay.
Okay. Associated to eccentricity, there are 2 concepts: core of a network and periphery of a network. Look at the core. What is the core? The nodes that have minimum eccentricity. Okay? All these have eccentricity free. It's like the center, okay? These 8 nodes of the karate network are like the center or centers of the network, okay? Periphery, look the periphery, are the nodes who had maximum eccentricity, 5. Okay? Okay? Look. Here. I display the network. Good luck. I display the network in a perfect way. Periphery, core. You know that a synonym of core is center, no? Center. Okay? Questions? Okay. Important concept I forgot. Giant component. Okay, let me show another network because this is connected. It's a very simple and very important concept. Oh, okay. Giant component. This. It has 4 nodes. This has three, this has two. Giant component. When we next week we're going to talk about random networks, the first important historic model of networks. One of the important things of network models is the existence of giant components. When we talk about the random networks, it's a model of networks. This notion is very, very important. What else we have here? Okay, let me, if I can show you the key core. What else? Okay, look here, a detail. Let me show the karate Olegara. Let me show this network, this other network. Okay. Look, density is 0.09, very low density. Here, I am showing you what is the maximum number of links this could have. It's n times n minus 1 over 2, where is number of nodes. This density is what? The links of the network divided by the maximum links. 27 divided by 300 is 0.009, okay? Is the way to calculate the density. Let me try the K-core to see if you could guess what is the key core. Look, here I put the key core 0. Click, nothing happens. Key core 1. Click, nothing happens. Key core 2. Click, look, disappear. Key core 3. Click, disappear. Key core 4. Click, out. Do you understand what is the key core? It's a very simple concept and a very important concept. Look, key core 0, eliminate nodes with degree 0. No nodes. Key core 1, eliminate nodes with degree 1. No, I'm wrong. Forget about it. This button is incorrect. I explain next class. Pico. Okay. No, I have time. Let me explain it in Gephi. I'm going to try to load the network that I couldn't load in NetLogo. Let me see if I can find it. Oof, complicated. No, I guess no. Okay.
Professor?
Yes?
Maybe key core is related with eccentricity, yeah? Maybe, or not?
Alex is doing the question?
Yeah, I am talking. Maybe key core, is the eccentricity is related with that measure or not?
Okay, it's a very good question. I have not thought of that, of the relation between eccentricity and key core. It's very probable that there exists a near relation between those two concepts. Let me show you the key core in Gephi, and later we talk about your question, Alex, okay? Okay. Let me see if I could Okay. Guys, this is the protein network that I couldn't show in NetLogo. Look, this is important. Look what is going to happen when I click this. Okay, before 200 nodes, nearly 300 edges, links. Look, please. Explodes. Okay? This network explodes. How many components have this network? Difficult to say it. Okay? Difficult to say it. But Gephi, look, connected components have the answer. Undirected. 185 components. Okay? Giant component. Let me, if I can show you. I don't remember. No. Okay, the giant component is here. But I'm interested in, I forgot. In what I was interested? Please remind me.
Keycore.
Keycore. Thank you. Filters. Okay. Keycore. Look. Keycore. Look. Filter. Value here. Keycore 1. Nothing happened. Keycore 2. Okay. Keycore 1. Keycore 2. Keycore 3. Keycore 4. Keycore 5. We're going to the core. That's why it's called K-core. In K steps, we're removing nodes with low degree. Gradually, nodes with degree 1, with degree 2, and what survives? The nodes with high degree. So we are going to the center of the network. Okay? Look. Center. Disappear. Center. I can isolate this core. Is the nucleus. These are the nodes with most degree in the network. Okay? Here they are. Okay, there are communities. Okay, let's calculate communities. Modularity, run, communities. How many? Free communities. Let's color the communities. Gephi, it's spectacular. Give and who? The best. Huh? Oh, I cannot see very well the communities. Let me. No. Okay, expansion. Okay. K-core. Okay, I'm going to stop here. I'm going to say only one last thing. There are a lot of global measures. These are 5, 6. There are more global measures. These are the most important. We are not going to talk more about local and global measures. But if there's a next session question, we could answer. We are next session is going to be a very important session because we are going to talk about network models. It's a central topic of network science. So thank you for your patience. thank you for your attention. And Luis Fernando, thank you for all. And see you next week, guys. One thing, excuse me. To all the girls in this session, a very good day. Today is Women's Day, okay? A very good night for the girls, for the women.
And for everyone else, right?
Okay. Yes.
Good evening.
Thank you for the compliment.
Thank
Okay.
you.
Good night for you all.
Okay. Good evening.
Bye, goodbye. Thank you.
Bye.
Thank you.
Thank you.
Bye now.
Thank you, Professor.
Bye.
Okay.